A two-lane road climbs the western face of Cheyenne Mountain, 10 miles south of Colorado Springs, Colorado. The road passes through ponderosa pine and scrub oak. It looks like the entrance to a state park. Then you round a curve and there is a checkpoint, and behind the checkpoint, a tunnel bored straight into the granite. And at the end of the tunnel, two blast doors, each one 3.5 feet thick, each one weighing 23 tons, mounted on rails so they can swing shut in less than 45 seconds. Behind those doors is a city. 15 buildings, 5 acres, 6 million gallons of water stored in pools carved from living rock, 500,000 gallons of diesel fuel, a medical clinic, a dentist, a chapel with a non-denominational chaplain, a convenience store, a gym that converts into a hospital when the doors close, power generators that can run for weeks without resupply, air filtration systems designed to scrub out radioactive fallout, chemical agents, and biological weapons. Between 300 and 600 people work here every day. They eat here, exercise here, worship here. Some of them have families who live in Colorado Springs, 10 miles down the road, and those families have always known, that if the blast doors ever close for real, the people inside the mountain will survive, and the people outside the mountain probably will not. That is the bargain. That has always been the bargain. This place exists because in 1957, the Soviet Union put a satellite into orbit, and the United States of America realized it had no way to see what was coming. The problem predated Sputnik. It began with bombers. In the late 1940s, the Soviet Union developed the Tupolev T-4, a reverse-engineered copy of the American B-29 Superfortress, built from 3 B-29s that had made emergency landings in Soviet territory during the war against Japan. Stalin had ordered his engineers to duplicate the aircraft down to the last rivet. They did. The T-4 could carry a nuclear weapon, it could reach the continental United States from bases in the Soviet Arctic, and the United States, in 1949, had no reliable way to detect it coming. The radar networks of World War II had been designed to watch the coastlines for incoming aircraft. They were short-range, low-altitude systems pointed outward from the population centers of the east and west coasts. But the Soviet approach would not come from the east or the west. It would come from the north, over the Arctic, over Canada, across the vast, empty, unmonitored expanse of northern airspace where no radar station existed and no fighter interceptor was based. The response was the distant early warning line, the DEW line, a chain of radar stations stretched across the Arctic from Alaska to Greenland, built in the mid-1950s at enormous expense, staffed by men who lived in some of the most isolated and inhospitable conditions on Earth. The DEW line could detect incoming bombers, but detection was only half the problem. The other half was response. Once a radar operator in the Arctic saw a blip on his screen, what happened next? Who did he call? How did that information reach the people who could order interceptors into the air, who could alert the Strategic Air Command, who could authorize the retaliatory strike that deterrence theory demanded? The answer, in the early 1950s, was confusion. There was no centralized command, no single facility where the data from every radar station, every tracking system, every early warning network converged in real time. Air Defense Command existed, headquartered at Ent Air Force Base in Colorado Springs, but it operated from above-ground buildings that were vulnerable to attack and connected by communication systems that were vulnerable to disruption. The entire air defense of North America was, in the language of military vulnerability assessment, soft. A single Soviet nuclear weapon detonated over Colorado Springs would destroy the command center, sever the communications, and leave the rest of the defense network blind, deaf, and leaderless. General Earl Partridge, who commanded the Continental Air Defense Command, understood this vulnerability with a clarity that kept him awake at night. On January 15, 1956, he stood in front of the Ent Air Force Base headquarters, a perfectly ordinary office building, and thought about what a 20-megaton hydrogen bomb would do to it. The building would not merely be destroyed, it would cease to exist. The concrete, the steel, the electronics, the people, all of it would be converted to plasma in the first microsecond of detonation. The command center of North American air defense would be gone before anyone inside it had time to process the warning that the attack was underway. Partridge needed a command center that could survive what was coming. Then, Sputnik changed everything. On October 4, 1957, the Soviet Union launched Sputnik 1 into low Earth orbit. The satellite was a polished metal sphere, 23 inches in diameter, broadcasting a radio signal, beep, 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 that anyone with a shortwave receiver could hear. The sound was harmless. The implication was not. If Moscow could put a satellite into orbit, Moscow could put a nuclear warhead on a ballistic trajectory that would reach the United States in 30 minutes, not hours, not the time it would take a bomber to cross the Arctic. 30 minutes, from launch to detonation. Half an hour between the existence of American civilization and its annihilation. The bomber threat had been serious. The missile threat was existential. A bomber could be intercepted, a fighter could shoot it down, an anti-aircraft battery could bring it down. The DEW line gave hours of warning. Hours was enough time to scramble interceptors, disperse strategic air command bombers, and prepare. But a ballistic missile traveling at 15,000 miles per hour, arcing through the upper atmosphere on a trajectory that no interceptor could reach and no anti-aircraft gun could touch, that was a different kind of threat entirely. The United States needed two things simultaneously. It needed a system to detect and track incoming missiles, a system that did not yet exist, and it needed a place to put that system that would survive the very attack it was designed to detect. Because the Soviets were not stupid. If they launched a first strike, the first targets would be the American command and control centers. Destroy the brain, and the body cannot respond. Destroy the eyes, and the body cannot see. The command center had to survive the attack, or the detection system was useless. NORAD, the North American Aerospace Defense Command, was formally established in 1958 as a binational partnership between the United States and Canada. Its mission was to provide aerospace warning and control for North America. Its headquarters remained at Ent Air Force Base. Its headquarters was still soft. The search for a hard alternative led planners to Cheyenne Mountain. Cheyenne Mountain is a triple-peaked massif of Precambrian granite, roughly 9,500 feet high, composed of rock that is approximately 1.7 billion years old. The granite is dense, hard, and remarkably uniform, exactly the kind of geological formation that absorbs blast energy and thermal radiation. 2,000 feet of solid rock above the planned facility would provide shielding that no amount of reinforced concrete could match. The mountain was close enough to Colorado Springs to be operationally connected to existing military infrastructure and remote enough to be a separate target from the city itself. The decision to build inside the mountain was approved. The Utah Construction and Mining Company won the excavation contract on May 2, 1961. Work began 16 days later, on May 18th. At the official groundbreaking on June 16th, General Lawrence Cooter, the second NORAD commander-in-chief, set off a symbolic dynamite charge. The real dynamite had been going off for weeks. Over the next 3 years, miners blasted and excavated 693,000 tons of granite from the interior of Cheyenne Mountain. That is approximately twice the weight of the Empire State Building, removed 1 truckload at a time through the single access tunnel. The work was done by hard rock miners, men who had spent their careers boring through mountains for mines and highways and railroad tunnels. They drilled blast holes, packed them with explosives, detonated the charges, and then hauled the shattered rock out through the access tunnel in dump trucks that ground their brakes on the steep grade and filled the tunnel with diesel exhaust that the ventilation system struggled to clear. The noise was continuous, drilling, blasting, hauling, day and night, 7 days a week. The mountain shook. The residents of Colorado Springs, 10 miles away, occasionally felt the tremors. The excavation created a series of interconnected chambers, 3 main tunnels, and several branching caverns, large enough to house the 15 buildings that would comprise the operational complex. The main chambers were enormous, some over 40 feet wide and 3 stories tall, carved from solid granite with a precision that the miners' civilian experience in mining and tunneling had not required. The walls had to be smooth, the floors had to be level, the ceilings had to be structurally sound enough to support their own weight without additional reinforcement, except where the rock had other ideas. In August 1962, a geological fault was discovered in the ceiling of one of the main intersections. The crack ran through the granite at an angle that threatened to drop a section of ceiling onto the work below. The fix required a massive reinforced concrete dome, adding $2.7 million to the project cost and several months to the schedule. President Kennedy visited NORAD in June 1963 for a briefing on the construction status. The architectural design was created by Parsons Brinckerhoff, a firm better known for designing bridges and subway systems, but a mountain bunker, it turned out, had more in common with a subway tunnel than with any above-ground building. The excavation was complete on May 1, 1964. Then, the real engineering began. The buildings inside Cheyenne Mountain do not sit on the rock floor. They float. Each of the 15 structures, 8 three-story buildings and 3 two-story buildings plus support facilities, is mounted on enormous steel springs, 1,319 springs in total, each one weighing roughly 1,000 pounds, designed to absorb the shockwave of a nuclear detonation and isolate the buildings and their contents from the ground motion that would otherwise tear them apart. The springs allow each building to move up to 18 inches in any direction, a slow, swaying motion that would be imperceptible to the people inside during normal operations, but that would become the difference between survival and destruction during a nuclear near-miss. The blast doors, those 23-ton steel and concrete barriers at the tunnel entrance, can seal the complex from the outside world in under 45 seconds. Once sealed, the complex operates on its own power, its own water, its own air supply. The air filtration system can remove radioactive particles, chemical warfare agents, and biological contaminants from the outside air and deliver clean, breathable atmosphere to the occupants for as long as the diesel fuel holds out. The water, 6 million gallons, is stored in 4 excavated reservoirs within the granite, enough to sustain the population of the complex for weeks. The total cost of construction was $142.4 million in 1961 dollars, approximately $1.6 billion in today's money. The complex became operational on April 20, 1966, when NORAD transferred its Combat Operations Center from Ent Air Force Base to the mountain and declared the system fully functional. On February 6, 1967, all systems, the Space Defense Center, the Missile Warning Center, the Air Defense Operations Center, were declared fully operational. America's brain had moved inside the mountain, and from that moment forward, someone inside that mountain was watching the sky, every second of every day, looking for the thing that must never come. The watching was done with technology that evolved constantly and was never quite fast enough. The Ballistic Missile Early Warning System, BMEWS, was the first dedicated missile detection network. 3 massive radar installations at Clear, Alaska, Thule, Greenland, and Fylingdales, England, pointed northward toward the Soviet Union, scanning for the infrared signatures of rocket launches and the radar returns of warheads arcing through the upper atmosphere. The data from BMEWS flowed to Cheyenne Mountain through hardened communication lines. Bell Laboratories' Close-In Automatic Route Restoral System, a blast-resistant telecom network buried hundreds of feet under granite with multiple redundant pathways between remote relay stations 30 to 120 miles from the complex. Inside the mountain, Burroughs Corporation computers processed the incoming data. The electronics could evaluate aerospace surveillance information in 1/millionth of a second. The humans who interpreted the computer's output had somewhat longer, but not much. From the moment a Soviet ICBM launched from its silo in Siberia, the crew inside Cheyenne Mountain had approximately 25 to 30 minutes before the warhead arrived. In that time, they had to confirm the launch, assess the number and trajectory of incoming warheads, communicate the warning to the National Command Authority, the President and the Secretary of Defense, and provide the information necessary for a retaliatory strike. 25 minutes. The time it takes to cook dinner. the time it takes to drive across a small city, the time between the beginning of the end and the end itself. Every person who worked inside Cheyenne Mountain understood that their job, reduced to its essence, was to ensure that those 25 minutes were used correctly, that the warning reached the right people, that the assessment was accurate, that the response, if it came, was proportional and directed, and not the result of a computer glitch or a radar return or a flock of geese that a processor somewhere had confused with a salvo of nuclear warheads. That last scenario was not hypothetical. On multiple occasions during the Cold War, the warning systems generated false alarms that looked, for minutes that stretched like hours, exactly like a Soviet first strike. On November 9, 1979, a training tape, a simulation of a Soviet ICBM attack used for routine exercises, was accidentally loaded into the live warning system. For 6 minutes, the screens inside Cheyenne Mountain displayed what appeared to be a full-scale Soviet nuclear assault on the United States. Fighter interceptors were scrambled from bases across the northern tier. The President's National Emergency Airborne Command Post, a specially modified Boeing 747 designed to serve as a flying White House in the event of nuclear war, began preparations for emergency takeoff. Strategic Air Command bases went to heightened alert status. For 6 minutes, the chain of command was operating on the assumption that the missiles were in the air. The error was identified when operators cross-checked the BMEWS radar data and the Defense Support Program satellite feeds. The radars showed empty sky. The satellites showed no launch plumes. The attack existed only inside the computer. The training tape was removed. The alert was canceled. The interceptors landed. The world continued to exist, unaware of how close it had come to a response triggered by a software error. Then it happened again. On June 3, 1980, at 2:26 in the morning, the displays indicated a massive Soviet launch. 2,200 incoming warheads appeared on the screens. The duty crew initiated the Threat Assessment Conference, the first step in a sequence that could end with retaliatory nuclear launch. Strategic Air Command bomber pilots at bases across the country ran to their B-52s and started engines. Minuteman missile crews in underground silos in the Dakotas and Montana began their launch preparation checklists, verifying codes, inserting keys. Then the numbers changed. The display flickered. The warheads disappeared, then reappeared, then disappeared again. The data was not consistent with a real attack. A real launch would produce a coherent, stable track that correlated across multiple independent sensor systems. This was noise, electronic noise, generated not by Soviet missiles, but by a faulty computer chip inside the warning system. A 46-cent integrated circuit had failed in a way that mimicked the end of the world. The alarm was resolved in minutes. The bombers shut down their engines. The missiles stayed in their silos. The world continued. But the incident revealed something that the builders of Cheyenne Mountain had understood from the start. The greatest threat was not necessarily the enemy. The greatest threat was the system itself. The possibility that the machinery built to prevent nuclear war could, through malfunction, trigger one. The crews inside the mountain lived with this knowledge every shift. Their job was not merely to detect an attack. Their job was to determine with absolute certainty in the span of minutes whether an alarm was real. Because being wrong in one direction, failing to detect a genuine attack, meant national destruction without response. And being wrong in the other direction, reporting a false alarm as real, meant national destruction by response. The margin for error was zero, and the tools they used were built by humans who could not build to zero-error standards. That gap was the most dangerous space in the Cold War. The Cold War ended. The Soviet Union dissolved in 1991. The existential threat that had justified hollowing out a mountain and spending the equivalent of $1.6 billion receded. Not entirely, but enough that the question arose, does America still need a command center inside a mountain? In 2006, NORAD and U.S. Northcom relocated their primary operations to nearby Peterson Air Force Base. Cheyenne Mountain was redesignated as an alternate command center, warm standby, continuously staffed, but no longer primary. The move made logistical sense. Peterson was easier to staff, easier to maintain, and more connected to modern digital communication infrastructure. The mountain, with its 1960s-era tunnel access and its physical isolation, was expensive to operate and increasingly difficult to modernize. But the mountain did not close. It never has. Between 350 and 580 people work inside it every day. The blast doors can still seal in 45 seconds. The springs still hold the buildings 18 inches above the rock floor. The water still sits in its granite pools. The diesel generators still wait. The reason is simple and has not changed since 1957. The threats have changed, from Soviet bombers to Soviet ICBMs to Russian ICBMs to Chinese ICBMs to hypersonic glide vehicles to electromagnetic pulse weapons to cyber attacks that could disable every unshielded electronic system on the surface. But the fundamental vulnerability that General Partridge identified in 1956 has not changed. A command center on the surface can be destroyed. A command center inside a mountain cannot, or at least cannot be destroyed as easily, as quickly, or as cheaply. The granite does not care about technological progress. It does not care about budget cycles or defense reviews or the shifting priorities of the Pentagon. It is 1.7 billion years old. It was there before the Cold War, and it will be there after whatever comes next. The buildings inside it may be updated, the computers replaced, the communication systems upgraded, but the rock remains. And as long as the rock remains, there is a place where someone can sit behind 23-ton blast doors, watching the sky, waiting for something that must never come. On September 11, 2001, when hijacked aircraft struck the World Trade Center and the Pentagon, NORAD locked down within minutes. NORAD's commander implemented Operation Noble Eagle from inside the mountain, the emergency air defense posture that the military had never needed to execute in a real-world scenario. The mountain's computational systems turned to tracking every commercial aircraft in American airspace simultaneously, coordinating with the FAA to identify which planes were still in the hands of their pilots and which were not. The mountain had been built for a Soviet nuclear strike. On that September morning, it was used to defend against 19 men with box cutters. The threat had changed beyond anything the original designers had imagined. The mountain still worked. Today, the Cheyenne Mountain Complex is owned and operated by the United States Space Force. NORAD and U.S. Northcom use roughly 30% of the forespace and account for 5% of the daily population. The rest of the facility belongs to missions that did not exist when the excavation began in 1961. Space surveillance, cyber defense, electromagnetic spectrum monitoring. The mountain's greatest advantage in the modern era is one that its designers could not have anticipated. It is naturally shielded against electromagnetic pulse. An EMP weapon, a nuclear detonation at high altitude designed to destroy electronics rather than people, would disable every unshielded computer, every unshielded communication system, every unshielded piece of electronic equipment across hundreds of miles. The surface world would go dark. Inside the mountain, behind 2,000 feet of granite and Faraday cage shielding, the systems would continue to function. The eyes would remain open. The brain would remain alive. This is why the mountain cannot be closed. This is why it will never be closed. Not because of what happened in the past, but because of what might happen in the future. The specific threats will continue to evolve. The bombers will be replaced by missiles, the missiles by hypersonic vehicles, the vehicles by weapons that have not yet been imagined. But the fundamental problem, the need for a command center that can survive the attack it is designed to detect, will not change. It cannot change. It is inherent in the logic of deterrence itself. The mountain is the answer.
It has been the answer since 1957, when a polished metal sphere in orbit over the Earth beeped a signal that told America its oceans were no longer wide enough and its skies were no longer safe. The response was not a weapon. It was not a shield. It was a hole. A 5-acre hole carved into 1.7 billion-year-old granite, fitted with springs and blast doors and diesel generators and 6 million gallons of water, staffed by people who go to work every day knowing that their job is to watch for the thing that ends everything. They have watched for 60 years. They are watching now. Inside the mountain, behind the doors, someone is looking at a screen, reading the data, assessing the sky. The sky is clear. It has been clear for 60 years. The mountain was built so that it stays that way.